Okay, everyone. Thanks for being flexible with this week. This week, we are going to learn about correlation. So correlation is how we connect multiple variables together, and we that correlation doesn't necessarily imply that one variable or one thing causes another thing, but it does say that they are connected to one another. They happen at a similar time. So correlation is kind of one of the antecedents or the lead up concepts to regression, which is what we'll deal with next week. So this week's a little different. It's all online. So I'm going to introduce correlation here in this video, and you can consume it in multiple chunks if you would like. And I'm going to then have a separate video where I show you how you can calculate correlation matrices in Excel. So the data will be up on Canvas that you can use, and it's actually from an NSF-funded research project on land conflict and deforestation. And we can look at some correlation coefficients that show the strength of the relationship. And then I'll do also in that Excel video a little bit of scatter plotting, just so that we can see one of the other ways to diagnose correlation. So anyway, this is a little bit different than our normal class thing. There will be two videos for this week. This one, which explains the concepts, and another which shows the implementation in Excel. And then next week, we'll pick up with beginning bivariate regression, which will be really great. You can contact me via the normal channels. During this week, I will be in touch. I just won't be available in person. All right, so to correlation. So correlation and causation aren't the same thing, as this Dilbert cartoon shows. Just because somebody is very smart but only sleeps a little bit, or makes a lot of money but only sleeps a little bit, doesn't mean if you start behaving the same way that you're going to make a lot of money or be a genius. And so that's kind of the crux of correlation, is that it kind of hints towards causation without actually allowing you to say anything specific about causation, right? So correlation is a possible connection between two variables. It's not a guarantee, but we can look at correlation as something like it kind of suggests or gestures toward causation. So it's definitely true that things that are caused by something else correlate with that thing that causes them, but it's not true that things that correlate are necessarily linked by causation, right? So this XKCD comic strip kind of hits the nail right on the head, right? I used to think that correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe, right? Other things could have led the stick figure on the right to decide that correlation does not imply causation, but probably a stats class helped, right? So correlation, the word correlation can mean two things. It can mean a statistic, which describes the amount of relationship between two variables, or it can be on its own a word that indicates there's a relationship. So we use correlation to describe both a numeric value and just a general relationship, right? It's a term that describes a general relationship between two variables. So some foundational concepts for correlation. Correlation actually requires two types of variables. The first one is a dependent variable, and this is the variable that you're usually interested in understanding what might be leading it to happen, or what might be associated with its occurrence, right? So this dependent variable is a variable whose values are influenced by other variables. So something like maybe a vote in political elections might be something that you're interested in understanding what is correlated with a vote for a certain candidate, right? Do candidates who like to eat donuts on Saturdays vote typically for people who want to raise taxes, for example, right? Another example might be blood pressure. Classic correlation with high blood pressure is high salt intake, right? So we know that salt actually does cause high blood pressure. We could look for that relationship, or we could be looking to predict high blood pressure. It's not just salt, though, that leads to high blood pressure, right? Gas mileage is another one. We know that cars get better gas mileage when they weigh less, when they have smaller engines, maybe when they accelerate less rapidly, right? So we know things that might lead to better gas mileage The dependent variable itself, though, is the one whose values are influenced by these variables like engine size or vehicle weight. And so gas mileage would be a dependent variable in this case. So this is usually the variable you're trying to explain the values of through some other set of variables. Now, the other type of variable is going to be your independent variable. So this is a variable whose values might influence the values of the dependent variable. So think about vote in political elections might be your dependent variable, but the economic status of the voter or their religion might be the independent variable. So their vote in a political election probably isn't driving their economic status, mainly because it seems like many Americans vote against their economic best interests, or their vote in political elections is not necessarily determined by their religion, because theoretically we're supposed to be separating church and politics, right? Anyway, there's also, the independent variable in this case isn't necessarily determined. It isn't determined at all by the dependent variable, but it can help determine the value of the dependent variable, right? Away from social issues, salt intake or genetics might be the things that drive blood pressure. Blood pressure is not changing your salt intake. It's not changing your genetics, right? So the independent variable is independent of the values of the dependent variable. That's why we call it the independent variable. For the gas mileage, driving style, vehicle weight, these are independent variables that might determine or help determine or influence, or maybe not. They're just correlated with the dependent variable. So over here in our graphic, we have a list of independent variables and dependent variables, and these are linked by some term. And these are kind of the types of relationships you might talk about when we talk about correlation. So an independent variable might be the magnitude of an earthquake. The dependent variable, which depends partially, perhaps, on the independent variable, might be the damage. So magnitude of an earthquake influences the damage that is caused by the earthquake, right? The amount of gas in a car relates to the number of miles driven by that car, or the time which passes, independent variable, affects the amount of bacteria in a culture, the dependent variable. So we got two types of variables correlation requires them. We have a dependent variable and an independent variable. When we test correlation, which is going to seem really similar to the hypothesis testing we've been doing with z-scores and t-scores over the last few weeks, we have two different hypotheses. We have the null hypothesis, this h sub 0, that there's no relationship between the dependent variable and the independent variable. So an example might be salt intake has no influence on blood pressure. That would be the null hypothesis. Now, just like with t-tests and z-tests, the null hypothesis may clearly be wrong, or may be very clearly probably not true, right? But we are testing it against an alternative that's really what we're interested in. And if that alternative isn't true, we have to accept the null, right? The null is supported, right? So an alternative, an example of an alternative hypothesis might be that there's a relationship between dependent variable and independent variable. So salt intake influences blood pressure, or salt intake increases blood pressure, or salt intake decreases blood pressure. These could all be alternative hypotheses, right? So usually the null hypothesis is there's no influence, there's no relationship here. And usually the alternative is that their hypothesis is that there is a relationship, or that the relationship is positive or the relationship is negative, meaning increases the dependent variable or decreases the dependent variable. All right, so let's do an example with height and self-esteem. So researchers in both physiology and in psychology have noticed that there is a correlation between the height of an individual and their self-rated self-esteem, right? And so this is a question that comes up from time to time, and it's maybe questionable. There are probably other things that height influences that leads to better self-esteem, but I'm not really a researcher in this area, so we'll just take this example at face value, right? So the research question might be, does height influence self-esteem? And the first step we have to do here is figure out whether what is the independent variable here and what the dependent variable is, right? So in this case, we might, if the question is, does height influence self-esteem, our independent variable and dependent variable are built into this research question, right? Because self-esteem is got to be influenced by, in this research question, right, height. So self-esteem is that dependent variable because it is influenced by height, right, which is our independent variable. Self-esteem probably doesn't make somebody grow taller. And so therefore, height is going to be that independent variable, and self-esteem will be the dependent variable. And here's the histograms for these. We have height measured in inches on the left for our independent variable, and we have our self-esteem measured on the right on a scale of 1 to 5, with 5 being the highest self-esteem. All right, so we look at our summary statistics here, and for height, we have a mean of 65.4 with a standard deviation of 4.4 inches. The shortest person is 58 inches tall. The tallest one is 75 inches tall. And there's a range of 17 inches between smallest individual and tallest individual. Or I should say, instead of smallest individual, I should probably say shortest, right? Then on the 1 to 5 self-esteem scale, the average is 3.75 out of 5. The standard deviation is 0.42 points on that scale. The minimum rating is a 3.1 and the maximum is a 4.6, giving us a range of about 1.5 points there on that 1 to 5 scale. So just to give you an overview, here's the distribution and here are the summary statistics. All right, so one straightforward way to investigate a relationship is a scatter plot. So a scatter plot is set up so that the x-axis here has height of the individual on it as measured in inches, and the self-esteem scale is here on the left, measured on a scale of 1 to 5. Now remember, our lowest value in that scale is 3.1, our highest is 4.6. So we won't have the whole 1 to 5 scale in this scatter plot, although if you made it in Excel, it could, right? All right, and so what do we notice? There's a tendency here when we have a tall individual like this 75-inch tall individual, they have a pretty high rating of self-esteem here, maybe 4.3 or something like that, right? Same here, our highest ratings tend on that self-esteem scale up above 4 tend to be the taller individuals, and the lower ratings on the self-esteem scale end up being the shorter individuals in this data set. And so what we notice is that as height goes up, self-esteem also seems to increase, right? So that's a scatter plot. It'll give us a comparison of the two values, and we can see where the clustering happens or whether there's an upward trend as one value gets tall or high, rather, the other one does as well. Or we can have negative kind of tendencies here where one value gets high, the other one gets lower, right? We can do this more numerically as well, and we can calculate something called R, which is the correlation coefficient. We actually sometimes will call this the simple correlation coefficient or just R, the R value, right? And there are less simple correlation coefficients, but we'll focus on R for this class, R and another one for certain ranked variables, like those ordinal variables that you might be familiar with. But the R equation here, it's another one of these that looks kind of gnarly, but it's not that bad. So basically N is the number of paired observations we have. We have to pair them because we are comparing, say, height and self-esteem. And so we need one observation for each of the two variables we want to investigate the correlation of, right? So N would be the number of paired observations. If you have 15 observations of height and 15 observations of self-esteem, that would be 15 paired observations. And notice it's not a lowercase n, it's a capital N because this is a different value, right? Then we have these summations. So the summation sign of xy is the sum of the product of paired observations. So if you had a self-esteem of 1.5 and a height of 60, you'd be 1.5 times 60, which would be 90 inches, right? So that's anytime you see the summation symbol here, this weird looking Greek E, right, with xy, you're going to take the product of x times y, which is, say height and self-esteem. You're going to multiply those together and then add up all those multiplications, right? That's going to be the value that goes in here. It's going to be the value, oh, that's the only place it is, right? The summation of x is the sum of independent variable observations. That'll go in here, it'll go in here and here, right? And then the summation of y is the sum of dependent variable observations. That goes in here and here and here, right? And then you do this math here. You plug in your values and do the math, and you get your R value, or your simple correlation coefficient value. Now, there are a few features of R. So R is an indicator, or sometimes we'll call this an index, and it's bounded by the values -1 and +1. Now, this is kind of nice because when the R value is positive, it has positive correlation, meaning that as one variable increases, the other increases. That's this situation here. It's also what we saw with the self-esteem and height relationship, right? When the value of the R coefficient is negative, we have negative correlation, which is the second example here, which shows that as our X increases, our Z value, or our Y value, sorry, decreases. So as our, maybe our independent variable increases, the dependent variable decreases, or vice versa. So a negative correlation here, right? We can also have no correlation. We have just kind of a random cloud of points. And this would be a situation where our R value comes out as a 0 or very close to 0. The only caveat here is that perhaps if we have an R value of 0, we have some nonlinear correlation. And I'm gonna reserve talking about nonlinear relationships until maybe the end of April, right? So you should be aware of them, but really you need to get a good handle on these techniques for linear relationships before we really jump into the nonlinear trends, because the nonlinear trends are just adjustments to the linear relationships here, right? So for most of these exercises, we can see that when we find an R value of 0 or close to 0, you can just assume no correlation until we start talking about nonlinear relationships. So there are a lot of scatter plots that can come out. So we can have, and so these are different relationships with different R values. So when the R value is 1, we have perfect positive correlation, meaning that we kind of have this nice 45-degree straight line through our data set. We can have, though, perfect correlation that's not perfectly at 45 degrees, but essentially we have a nice straight line when we have a value of 1. And that line is increasing, right? So this is the x-axis here, and this is the y-axis along here. And so we'd have positive correlation as X gets high, as our dependent variable gets high, our independent variable also gets high. We can have negative correlation that's very similar, except that it's a decreasing trend. But what's interesting is more these perhaps clouds of points here in these scatter plots that have different, this is a pretty high, 0.8 would be a high positive correlation value. A high negative correlation value might look like this, a negative 0.8. Maybe pretty weak correlation might be a 0.4. And so this looks like a kind of more amorphous cloud, but there's a little bit of a positive relationship in here. And then we can have our coefficient of 0, where we have literally random noise, right, or pretty close to it. Now, I mentioned back on this slide here that nonlinear correlations will have a value of 0. And so we can have pretty nice correlations here, but they're nonlinear. And so what we want to make sure is that one reason why we kind of investigate relationships that are correlational with both scatter plots and the simple R coefficient is scatter plots will show you if there's something funky going on, like these, kind of non-linear relationships, or, kind of more 3D space kind of situations, right? So, but in this class, you'll be mostly handling data in this upper 2/3 of the graphic here, and these are real correlation coefficients with these scatter plot trends. All right, so relating our hypothesis, which is that height and self-esteem are linked, right? We can calculate the correlation coefficient of this relationship as a value of 0.73. So it's relatively strong, or fairly strong positive correlation here. What we could say is that 73% of the variation in self-esteem, we'll leave that. We'll leave that to regression, right? So the R coefficient actually indicates that, there's a pretty strong, fairly strong positive relationship between self-esteem and height, right? Now, here's the thing. as our values have greater variance, we'll have more deviations away from this positive correlation relationship. And when we get further away, that's going to actually drag our R value down. As you know from here, we could have this still positive relationship in our scatter plot, but as we get more values kind of floating out into the zones away from that relationship line, right, we get a lower correlation coefficient. So if our data values were kind of spread out up in here and down in here, we would end up with a lower correlation coefficient. So when variance is large, we are not going to have as strong correlations, right? So our hypothesis, we can also hypothesis test with correlation coefficients, right? So in this case, we'd kind of formally state, you know, hey, our null hypothesis is there's no correlation, and our alternative hypothesis is that there is correlation. We could state other relationships, like there's positive correlation between height and self-esteem, or there's negative correlation between height and self-esteem, right? So, but a lot of times we're doing this two-tailed kind of test. There is a correlation between height and self-esteem. So we can do a typical T statistic for our R value. So it's a T statistic of R, so our T of R, right? And the equation is here. Notice we have an N minus 2 degrees of freedom. That is because we are calculating a T statistic of a correlation coefficient, right? And this correlation coefficient has it's the relationship between two estimates. But this is, when we calculate this using this equation, we end up with a critical T statistic for our R value, and the framework is exactly the same. So we could ask, is an R value of 0.73 significant? Should we accept or reject the null hypothesis that there's no correlation between height and self-esteem? Well, we can do this math right here, right? And we can come out with a T test statistic of 4.56. And we have N minus 2 degrees of freedom, right? So if we set an alpha value or a P value of 0.05, we can look up our T critical in this column here. And what we're asking is there no correlation, or is there some correlation? So this is a two-tailed test, right? So we split our critical, our probability, right, or our alpha value, and we find 20 minus 2 degrees of freedom gives us 18. Our critical T value is plus or minus 2.1. And our T statistic is 4.5, and 4.5 is greater than 2.1. So we reject the null hypothesis and accept the alternative hypothesis. There is a significant positive correlation between height and self-esteem, right? So we won't do a lot of correlation coefficient hypothesis testing, but it's possible, and it's not all that difficult, right? So if you ever find yourself messing around with correlation, you want to say, is this correlation significant? You can do that hypothesis test this way. All right. However, we have to also ask, is this finding actually significant? So there is a statistically significant positive correlation between height and self-esteem. And that seems to indicate that taller people have more self-esteem, but is that reasonable? And what we can ask is, does height actually cause higher self-esteem? And this is up for debate, because these tests only relate to whether the values are similar to each other, right? They correlate with one another. We really can't say that height causes better self-esteem. So this kind of leads to a caveat that in most data sets, a null hypothesis that R is not equal to 0 is probably not reasonable. It's just an arbitrary statement. So actually in a data set with a lot of variables, 135 and an N of 2058, the average correlation actually comes out to 41, meaning that on average in a very large data set, there's actually a positive correlation that's close to statistically significant, right, given the size of the data set. And so usually a null hypothesis, something like height correlates negatively with self-esteem would be a more appropriate one, right? But no matter what, no matter how you phrase these hypotheses, you can't get at causation with correlational methods. To get at causation with quantitative methods, you need to do one of two things, right? One of those is laboratory studies where you control all variables. And I'm talking about literally all variables except for the variable of interest. That's very hard for a problem like height and self-esteem, because you would need genetically identical individuals raised identically with identical nutrition, with identical psychological events in their life. Everything would have to be identical. And the only thing that would be allowed to vary would be their self-esteem and their height, right? And actually, you would have to control for height too. So that would be really difficult, and it would be absolutely unethical to do, right? The other way that you can get a causation with statistical methods is through econometric approaches like fixed and random effects modeling. And those are beyond even the graduate level stats courses in this department. They're very powerful methods. You can take advanced econometrics in the econ department to learn about some of them. They require a lot of data in order to execute, and then also a lot of arguing with people who refuse to allow statistics to say something causes something else. So the take-home message here really is that stats typically doesn't say something is caused by something else. Instead, statistics is about telling us what variables appear to covary and whether that covariance or that correlation is interesting mathematically, right? Okay, there are other types of correlation. Another one you should be aware of is Spearman's rank correlation. So this is for variables that are in order, ordinal variables. And also that means that it is a way to deal with nonlinear correlation. So Spearman's rank correlation is often presented as rho, which tests monotonic correlation, which is one that has variables that have a hump in the middle. So some examples of variables that are like this could include the GDP rank and internet connectivity rank variables from your hypothesis data set, right? So these are monotonic correlations, positive and negative, right? Spearman's rank correlation does this. Its interpretation is pretty much identical to Pearson's simple to the simple correlation coefficient. There's -1 if the two rankings are in disagreement perfectly, meaning the first is last and the last is first. 0 if the rankings have no relationship at all, and then +1 if the rankings are perfectly in agreement, right? And so the output is very similar. To calculate it, it is not too different than the simple correlation coefficient, and interpretation is the same. I put this here not because I'm going to have you do it, but just because you might come across a situation where you have monotonic ranking correlation that you want to approach. Okay, so that's the end of this. Switch over when you have a chance this week to look at our correlation Excel work. This is just a demo, but the data are there if you want to follow along and mess around too. There are a couple tricks and tips for Excel that could come in handy outside this context of correlation analysis. So definitely check that out. And I will see you next week in person. Thanks a lot.